Hello, so our first topic of the day is the Cayley Hamilton theorem, and this is a result that we're going to be using to understand the tests for observability and controllability and where those come from. But before we get onto that, I just want to sort of talk a little bit more generally about the Cayley Hamilton theorem, what it is, what does it mean, and so on, and give some indications for how you can use it to simplify derivations. So the Cayley Hamilton theorem is a result that concerns a square matrix, and in amongst all of this, the square matrix that we're interested in is A, and we're going to say that this matrix is n by n. And the Cayley Hamilton theorem is a statement about the characteristic polynomial of said matrix, and that's what's written out here. So the characteristic polynomial of a matrix is just the determinant of some polynomial variable. We've called it lambda now, we've been using s a lot, we use z in discrete time, whatever. This is just a polynomial variable. So we've got lambda I minus our matrix A. And so the determinant here, this is the characteristic polynomial of the matrix A, and it takes this general form here. So we have a lambda to the power of n plus some constant multiplied by lambda to the n minus 1, and so on all the way through to a constant term here. So this is the characteristic polynomial of a matrix, and what the Cayley Hamilton theorem says is that if you substitute the matrix into its characteristic polynomial, you get 0. So I'll just write out what we mean by that. And what we mean is if we replace our polynomial variable raised to the nth power, if we instead write our matrix raised to the nth power, so lambda to the n, instead we write a to the power of n, so that's just the matrix A multiplied with itself n times, and to that I add on this constant, so this is just a number, multiplied by the matrix A to the n minus 1, because we have a lambda n minus 1 there, and I keep doing that, and then right down to my constant term, so I have my C0 multiplied by lambda to the power of 0, and a matrix raised to the power of 0 is identity in direct analogy with the 1 by 1 case. So here I have this sum of matrices, everything's square, so this is a square matrix, this is a square matrix, this is a square matrix. If I add all of these things together, I get a matrix of zeros. So I'm just going to write this by 0 here, but we've got a square matrix of zeros here. And this is the Cayley Hamilton theorem. It says that if you substitute a matrix into its own characteristic polynomial, you get 0. And sometimes people say things like, the matrix satisfies its own characteristic polynomial, is a kind of a slick way to state the Cayley Hamilton theorem. So this is the Cayley Hamilton theorem. Just so that we're completely clear what it is, let's just do a simple 2 by 2 example. So let's just take the matrix 1, 2, 3, 4. So let's just say our matrix A is equal to this thing here, and let's just check the Cayley Hamilton theorem to see that it's true. So, well, we need to do a few things. We need to work out the characteristic polynomial for this matrix, and we also need to raise this matrix to various powers. So let's just, you can check this easily for yourself. If I take this matrix and I multiply it by itself, I get the matrix 7, 10, 15, and 22. Okay, so that's the matrix squared. So we've got various bits. The last thing we need to know is the characteristic polynomial for the matrix. So let's just write that out as well. So the determinant of lambda I minus A, and again, you can easily go away and check this for yourself. We get lambda squared minus 5 lambda, and minus 2. So this is the characteristic polynomial, and now all the Cayley Hamilton theorem tells us is that if we put a squared in place of lambda squared, and we subtract away 5 times our matrix, and then subtract away 2 times the identity, we should get 0. So let's just see. Lambda squared, well, we put in our a squared matrix, so that's 7, 10, 15, 22. And from that, we subtract 5 times this matrix here. So we're going to subtract away, well, 5, 10, 15, and 20. And from this, we're also going to subtract 2 times the identity matrix, which is just minus 2, 0, 0, 2. And then you can indeed see that 7 minus 5 minus 2 is 0. 10 minus 0 is 0. And so everything checks out. The Cayley Hamilton theorem holds for this one matrix at the very least. So that's what the Cayley Hamilton theorem is. Why is it going to be useful for us? So the main thing it allows us to do, that we're going to have repeated use for, is it allows us to take infinite series that involve powers of matrices and collapse them down into series that only involve powers of the matrix up to n minus 1. And to see how the Cayley Hamilton theorem lets you do this, let's just focus in on this equation. So it's one way to read this equation is that a to the power of n is equal to some sum of powers involving the matrix to the power 0 through to the power of n minus 1. So the Cayley Hamilton theorem lets you rewrite a to the n in terms of a to the 0 through to a to the n minus 1. And you can use this recursively. So we could equivalently multiply this whole thing by a, and the Cayley Hamilton theorem would show us how to write a to the n plus 1 in terms of powers of a to the 1 through to a to the n. But we know we can rewrite a to the n in terms of powers of a to the 0 through to a to the n minus 1. And so we can recursively apply this, and whenever we see a power of a with being raised to some power larger than n minus 1, we can always rewrite it in terms of powers up to the size of n minus 1. And we're in particular going to be using this to deduce properties about matrix exponentials. So the matrix exponential, so e to the at, this is just defined in direct analogy with the exponential, the 1 by 1 case. And so this is equal to the series identity plus at plus a half at squared, and so on. You write out this infinite series. You can go look it up in a data book or online or whatever. And so this is the definition of the matrix exponential, and this comes up very frequently in the, well, all the time, in the solution of our state space systems. If we want to write down the solution of a state space system in terms of its convolutions, we write it in terms of this matrix exponential. And we see from the definition that the matrix exponential just involves matrix A raised to higher and higher powers. And what the Cayley Hamilton theorem will let us do is, as soon as we hit our power a to the n, we can rewrite that in terms of all of these up to a to the n minus 1. And we can do the same with higher and higher powers of n. So the Cayley Hamilton theorem tells us that as long as this series is converging, that we can rewrite this as sum of between k0 and n minus 1, and some constants, let's just call them fk, a to the power of k. So we don't necessarily know what the constants are, but we know that there are some constants, so that we only need to consider powers up to the order of n minus 1. And what we're really going to use this for is, if you remember, you've seen these controllability and observability matrices for checking whether a system is controllable or observable, and perhaps you thought it was a bit mysterious that these involved powers of a up to n minus 1. But it will no longer be mysterious. We will cut through all of this with the Cayley Hamilton theorem, and it's all going to hinge on using simplifications like this for rewriting the infinite series in terms of some finite series where we need powers of a up to n minus 1. I thought we could finish just by doing another little example that shows where the Cayley Hamilton theorem is useful. And one thing that you can do with the Cayley Hamilton theorem is work out the inverse of a matrix in terms of powers of that matrix. And so we can use that to deduce we'll use that to deduce the formula for the inverse of a 2x2 matrix. So let's just go ahead. Let's say we have some square matrix A with entries A, B, C, and D, like this. The characteristic polynomial of this matrix, well, you can go and check it if you want, but so P of lambda for this matrix A is just equal to lambda squared. It's a 2x2 matrix. And then here we have A plus D times lambda. And then here our final term is plus, and it's the determinant of the matrix, actually. Here we have AD minus BC. And maybe you can see why we would expect the determinant to appear in our constant term. Our constant term can always be found by setting lambda is equal to 0. And if we set this equal to 0, well, we just have the determinant of minus a. And the determinant of minus a is equal to minus 1 to the power of n multiplied by the determinant of the matrix A. And again, I encourage you to go away and check that for yourself if you want further confirmation. So let's just sort of separate this off from our earlier calculation. So this is the characteristic polynomial of our matrix here. And now the Cayley Hamilton theorem is telling us that a squared minus a plus d a plus the determinant of a multiplied by the identity is equal to 0. And now let's just have a little think. What would happen if we multiplied this whole expression by the inverse of a? Well, we would find that minus the determinant of a multiplied by a inverse, so that's this term here but pulled onto the other side, this is equal to, and if I'm multiplying through by a to the minus 1, I would just have a minus a plus d. And that's, we just had a power of a there, so here we just have identity. So it seems something is a bit suspicious here, but maybe not. Let's just carry on and hope for the best. So a is just a, b, c, d. And from this, we're going to subtract a plus d multiplied by the identity. So here we just got a plus d on the diagonal, and we got 0 off the diagonals. And we've got a minus determinant of a, so let's just divide through by that. So this is all over minus the determinant of a. And hopefully you can see, if we just correct our minus signs like this, we end up with 1 over the determinant of a, and then the matrix we're left with here is just d minus b minus c a. And there we have the formula for the inverse of a 2x2 matrix that I hope you all recognize, but now derived by the Cayley Hamilton theorem. And in fact, we can use this trick in general to always rewrite the inverse of a matrix in terms of powers of the matrix itself. So here we have the Cayley Hamilton theorem, what it means, kind of a simple example, and also introducing this this feature of matrix exponentials that we're going to be using when we study observability and controllability.